Alright, this is my physics lab report for lab 3, black holes and orbits. So as an introduction, the purpose of the first part of this experiment was to find the mass of a black hole based on the motion of a star orbiting said black hole, of which we knew the mass. And the mass found was 1.2433 times 10 to the 24th kilograms. And this lab demonstrates Newton's second law of gravitation and its relationship with momentum. And additionally, in part 2, orbit don't crash, the objective was to calculate or to figure out what initial speed a rocket would need to orbit around a moon and planet in a figure 8 motion. Alright, so quick overview of Newton's second law. We just can say F net equals the change in momentum over the change in time, which you can separate that out into two separate components, this being P dp over dt and the magnitude of P dp over dt. Now this just translates to just the net force of being the force parallel plus the force perpendicular. And then for the net gravitational force, we can just say the gravitational constant times our two masses times the direction divided by the radius squared is also equal to, when configured with the net force, dB dt, equaling the general gravitational constant times mass 1, mass 2, or radius squared. And we can reconfigure that to get our second mass, or the black hole mass. Alright, so here's my GlowScript code. We have some initial constants that we have to cover, like big G always equals 6.7 to the negative 11th, but the mass of the star in this case is 2 times 10 to the 30th power kilograms. And the time interval needs to be converted, 24 hours needs to be converted into minutes, so you do 24 times 60 times 60. And then for our net force and velocities, we can look to the top right. We can see that P initial is the star's mass times the initial velocity, and the position final is the star's mass times the final velocity. You can see that we can calculate change in velocity, saying that the change in velocity equals the velocity final minus V initial. This is just simple kinematics. And then we can also say, if we're trying to find dP dt, we can just say that the delta P over delta T equals dP dt. And in this case, the only force in that direction is dB dt, so the F net equals dP dt. And then at the bottom, we can see that the F net perpendicular, the force in the perpendicular direction is just equal to dP dt perpendicular. Alright, so here's some of the mass values that running the GlowScript code came out with, and essentially these are all relative estimates or relative calculations based on the simulation and the position of the orbit. And so the way I found the mass of the black hole based on all these values was just take an average of them all. Alright, so now on to the second part, GlowScript code. Again, we have some initial constants. The gravitational constant is the same. Now we have masses, so we have the mass planet M, we have the mass of the planet, which is 8 times 10 to the 27th. We have the moon mass, which is 6 times e to the 25th kilograms. You can see and then the ship is 7 times e to the 12th, and then the time change is 60 minutes. So over on the right, we can see our equations for calculating our forces. We can see that the F net, the force on the moon is equal to just the force of the ship, the net force of the ship on the moon, plus the net gravitational force of the planet on the moon. And then we can see at the bottom the moon velocity is equal to the F net on the moon divided by the mass of the moon times the change in time, and the ship velocity is equal to the F net on the ship times the change in time. And this is the result of the attempts to make the ship orbit in a figure 8 motion. It didn't necessarily work, but I did get the ship to move while being interacted on by multiple. So for what if, what does it mean? How do parallel and perpendicular components of the net force differ from the rate and change of momentum? Because the parallel and perpendicular components are always in the same direction, and that's not necessarily what the direction that the rate of change of momentum is going in, because the components are two different components of a momentum at a given moment, not of a change of momentum. Now, if you wanted to predict the motion of an entire system, black hole, star, planet, moon, you would need to include the net forces of every single object on every single other object, like the a black hole on a star on a planet on a moon, and so forth. Yeah. Thanks for watching.